All right, welcome back everyone. Let's continue on with our discussion of concrete. And last time we talked about the formwork, transporting, and placing of the concrete. This time what we're going to look at is after it's placed, what can we do about, or what can we talk about with the curing, the setting up of the concrete, concrete accessories, reinforcing, and embedments. So let's start with the curing of the concrete. One of the most critical things is the fact that the surface of the concrete that it's exposed to the environment, can lose its moisture content, its water content. And of course, we know that water to cement ratio is important. So if we take out that water, we start to have these issues of cracking and spalling in the concrete, not doing well on the surface, right? Now this is the Menzel equation, and you can actually use that to calculate how much of your water is going to be lost based on some characteristics. So the way it works is if you had say this first one, it says air temperature 50. Well, I see this is air temperature in this upper left hand side. So I go to 50, which is like here, right, between 40 and 60. And then I follow the graph up until I reach the relative humidity of 50, which is between that 40 and the 60, so it's probably right about there. And then I move over to the right until I hit the concrete temperature, which is in blue. Well, my concrete temperature is 70. So I keep going over until I hit that 70 right here. And then I go down. So you're basically making like a big box, right? And I go down until I reach the wind velocity. In this case, the wind velocity is 5. So I go all the way down to 5. And then I can work my way back over, and finally that would be my loss. And I can see that I would lose about 0.1 pounds per square foot per hour. Now if I do the same thing, let's say it's a little warmer out. Let's say it's 90 degrees out. Well, that puts me right here on this first, let me get rid of the other stuff. That puts me right here on the air temperature. I'm going to go up till I hit the humidity of 40. So I go up until I hit this little red thing that says 40, right? And then from the red, I move to the right until I get to the temperature, concrete temperature of 100. So all the way over. And then once I reach the concrete temperature, I go down to the wind velocity, and we're going down to 20. Pretty quick wind. And once we hit that, then I can move on over and find out that I am at 0.6 pounds per square foot per hour. So it's 6 times greater water loss because I've increased the temperature 40 degrees and the wind, and also the relative humidity changed a little bit. So the point is that it is very sensitive. The concrete's very sensitive as far as the wind velocity and the air temperature. And what we need to do is we need to decrease those losses. So it's important, and we can even see this, that the issue is that we need to keep or the solution is that we need to keep our concrete humid, right? So we need to trap in that water, because we know that it's releasing all this water during this curing process. We talked about that. When this water reaches the surface, if we can keep it there and not have it evaporate out, then we get this stronger concrete. And that we saw this graph before about how if we don't keep it moist at all, we have this strength. The more we can keep it moist, say it's 7 days, we keep it covered and keep that moisture in there versus 28 days, versus if we can keep it in that moist cured environment the whole time, or moist while it's curing, I can see that I definitely increase my strength. So how do we do this? How do we lock in that moisture and keep it from going away? One way is by ponding, immersion. So you see this down here? Basically, it's like submerging your concrete in water. And many people think that concrete, you have to remember, concrete's a chemical reaction, right? So it's the chemicals that are reacting with each other. It's not like a drying out process. A lot of people think that. But of course, if you're underwater, it would never dry out, right? But it isn't a matter of drying, it's a matter of this chemical reaction. So we could submerge it, keep it underwater. We can fog it using a sprinkler, basically just constantly wetting it. We can use wet coverings like a burlap or cotton mat, something that's going to hold in water, and set it on top of the concrete to keep that moisture in there. Can use a paper to keep the moisture from sucking out and going into the environment, or plastic sheets, same idea. Liquid membrane, yeah, we can do that. But all of these methods have the same general idea, and that is just keep the concrete wet while it cures. So if we do have bad curing, you can see near the surface, this is where the real issue is, where this water was sucked out. And you get low durability, and you'll have a crappy concrete that'll always be spalding off the top and losing chunks. So it require more maintenance, and so bad things will happen. So the idea is to keep it all the way through from the top to the internal part, keep it as wet as possible while the curing is taking place. So let's move on and talk a little bit about reinforcing. We mentioned this last time that concrete is really strong in compression. So if I were to push on a concrete beam, it would be very strong. However, in tension, if I were to pull on concrete, it's very weak. And this is particularly important for what we see down here in the lower left if I have a beam, right? Because what happens if I load a beam is that the top half of this beam is all in compression, but the bottom half of this beam is in tension. It's being pulled apart. So we need to supplement that concrete with something to give it the extra strength. And the primary thing that we use is steel. So looking at this reinforcing, the two primary types of steel that we would use are either a welded wire fabric, like we see over here, or some steel rebar, some actual bars. And we'll talk more about those. When we speak of welded wire fabric, you can see some rolls of it over here. You can see it comes in various dimensions as far as the rectangular cross section, right? And you'll see this designation to name a welded wire fabric, like a WWF 6x12 W1.4 by W1.4. Now what that means is WWF is just saying welded wire fabric, so that's saying what it is. 6x12, 6 is longitudinal, 12 is transverse, so it's 6 inches one way, 12 inches the other. And then the W1.4 by W1.4, W is the type, meaning smooth. It's either going to be smooth or deformed. And what that means is smooth, well, you know what smooth means, right? It's perfectly smooth to the touch. Deformed means there's some ridges on there, something that'll catch more concrete, gives it more surface area. So this particular one would be a smooth surface, and then the 1.4 is the size of the little metal wire, and it's in hundredths of an inch. So this would be like 0.014 inches by another smooth 0.014 inches. So that's the naming process on something like that. Outside of welded wire fabric, we could also have reinforcing bars. Bars also come in either plain or deformed, meaning smooth, like I have down here in the lower left, or deformed. Deformed is what you're more commonly used to seeing, right? So with these little ridges on here, then those ridges, they improve that bond. You can imagine how it's clamping onto the concrete and it's making it so it doesn't want to slip through the concrete, right? And there's more surface area that's bonding with that concrete. And the rebar, you can see these designations on the rebar. It tells a little bit about the ribs in the mill, bar size, we'll talk about in a little bit, what kind of steel it's made out of. So when we talk about size, we'll talk about, like, say, a number 4 rebar or a number 9 rebar. Really all it is it's the size of the bar, say number 3, divided by 8 in inches. Meaning if I have a number 3 bar, then its diameter is 3/8 of an inch. If I have a number 8 bar, its diameter is 8/8 of an inch. Well, 8 divided by 8 is 1, so you should see 1 inch. Now that is the nominal dimension. It means it's what we name it. The actual dimension may vary slightly, but in essence, that's the naming convention for our bar sizes. Also note we have a weight in pounds per foot and a cross-sectional area, which of course you could calculate that if you needed to. When we are placing the rebar in the concrete, one important dimension is our overlap. And what this is if you have 2 rebars, you have the end of one rebar and you're starting another section of rebar, if you were to butt them end to end, then you have this, in essence, a joint, right, where you have no strength. So what you do is you overlap them so they become, once you tie them together, in essence, come one long continuous piece of rebar. The lap distance, the distance it has to overlap, is given in as a number of the diameters, meaning if I have, in this case, I have a number 4 rebar and I need an overlap of 20 Ds, then that means I know a 4 rebar is 4/8 or half an inch, and I have 20 times that, so 20 times a half is 10 inches, it means I need 10 inches of overlap for that rebar. This will be called out in the structural drawings, and some of it's based on the size of the rebar, the depth of the slab, and just what kind of reinforcement strength you need overall. So with this rebar, remember we have to support everything in these forms when we pour this concrete or place this concrete in the form, and we can't have our rebar sink to the bottom or hit the side, so we have to hold it in place somehow. And that's what this slide is really talking about with this reinforcing support systems. It's some way to hold the rebar, in this case, off the bottom of the slab. So there's these little, see these little metal things that go up like here, these little cone-looking shapes. These are called chairs, and these chairs are holding up the rebar as the concrete gets placed, and it holds it in place in the concrete. The reason we need that is because we can't have concrete too close to the bottom or any side of the slab. We need a concrete cover. The concrete cover gives protection to that rebar. Make sure that it's protected against the elements and not too close to any one side. And all that's specified by concrete design code. So the chairs will vary in height based on how far you need to keep it from the bottom of the slab. You can also have single or double chairs. Basically, a double chair just means it holds 2 pieces of rebar. You could also have lower high chairs, like I said. And the main point is for this, see the C minimum, that's our cover depth that we need. So our chair needs to be at least high enough to get us that, usually like about 2 inches away from the slab edge. Often our rebar will have bends. These are some typical bends. We might have a hook shape. We might have a 60-degree hook and a 90-degree bend. And a lot of these are used when you're moving from columns to beams. So you can see how this rebar is in this beam, and then we're transferring over to this column, right? And you can imagine how that gives it a rigid connection between the column and the beam. It also provides some shear strength, so it doesn't want to basically break off right there at the edge, and continuity between the horizontal and latitudinal stresses. And it sounds like you'll be working with these in your plan reading course, and my guess is you'll probably have to figure out lengths to order quantities and do takeoffs of materials and things like that. So just as this should be a reminder before you pour your concrete and it's all set in place forever, you do want to double check your size of the rebar, make sure you have enough steel in there to support the loading. Make sure your bending of the rebar is in the right place, like we said, and spacing between rebars, location of rebars. Make sure all of your splices are good and lapped, anchored firmly. I guess this is just a quick list of things you could double check before you pour your slab. Outside of rebar, the other thing that would be living in your concrete during this pour are embeds. Embeds will be like something that's embedded into the concrete while it's still in its liquid phase before it cures, and there's different reasons for them. I can see like right up here what this would be is a way to mount, like it might be like a steel column or something that has some holes in the flange, and then you can bolt it right to the concrete. And here's a side diagram of something like this, right? So like an anchor or a fastener. You could also have an embed, which is like a sleeve in essence. It's a hole through the concrete. We'll talk more about why we'd want to do this with these bands in just a little bit, but you might need the ability for something to move in and out of your concrete. Joint inserts. We talked about joints before if we're joining different sections together, and this might be a way that this concrete would join this little metal bracket here. Reglets. So this is a way to deflect water as it comes down. And there's other embeds, but those are just some common examples. Basically, just making sure all the embeds are in place and secure before you pour your concrete. All right, so moving on to somewhat of a different topic, this idea of precast concrete. So everything we talked about up to this point had us building forms, pouring the concrete into the forms, letting it set, removing the forms, something like that. And with a precast concrete, what it is it's actually cast away from where it's ultimately going to be. So there's two ways you can do that. One is site cast, so it's still on the same site as the construction, but it's not in the same place. Meaning usually, I think I have a slide that's coming up. It's cast on the ground and then tipped up into place is the most common for like a tilt-up wall, or plant cast, so cast in some plant far away and then shipped out to the site. So you'll see this a lot like on the back of these big semis that are traveling down the road with a big, looks like a twin T or a, we'll show some more shapes in just a little bit, but this precast idea of the concrete away at a plant and then shipped into the site. Some benefits is you get quality control because you're doing it right there on site. Same thing with the material consistency. Drawbacks, the more modular, meaning you're probably going to have the same shape over and over and over. And also, like I said, you see them traveling down the street, so you can only travel down the street with such a big size in the back of your semi, right? So there's definitely some restrictions to the size that we can bring out to the site. So one concept with these precast units is the idea of prestressing. What prestressing is a method to, like we said before, concrete is strong in compression, weak in tension, right? So if I were to bend the beam like this, then we have the bottom is in tension. The idea behind prestressing is what if, yeah, so I'm doing this and then the bottom is in tension. But if I were to push in the sides at the exact same time that I'm also bending it, then I'm putting it in compression, right? So if I push it straight in, it's in compression. And if I can push hard enough in and bend it at the same time or put my loading this way, what it means is the entire beam will be in compression the entire time, which is a strength when it comes to concrete, right? So there's two really methods we can talk about. One is pre-tensioning, the other one is post-tensioning. What pre-tensioning is you take this rebar, or it's actually just it's not really called a rebar anymore, it would just be a steel tendon, and you tighten it up really, really, really tight. So you pull it in tension, right? Then you pour your concrete slab. So this is the pouring of the concrete, and then you let out that tension. And what it does is it sucks the whole thing in, and it's pushing, like I said before, it's pushing on our beam, and it's giving it this compression force on our beam. The other way, remember we talked about embeds, we said you might want a duct through your, or a hole through your concrete. In this one, you cast it with a hole through it, then you put your steel tendon through here. After your steel tendon is through there, then you put a jack on it and you just crank it down. And this jack is then anchored, and then it just stays in place. So that provides us our compression on the post-tensioning side. So this is just a recap on the pre-tensioning. We're adding this high strength reinforcing tendons before the concrete is set, and then the tension is applied to wet concrete. Concrete is bonded to the tendons, and it locks into place, leaving that whole side in compression. Now this is usually used for like girders, T-beams, or columns. And this is the overall process once again, where I'm pulling the strand, pour the concrete, then I release the tension on that strand, putting the concrete beam into compression. And you can think about it, it actually shows this little bow, right? And that makes sense because I'm just pulling on so much it's bowing up. And then when I apply my load, the whole thing would end up being neutral, or in essence, there would be no tension in my concrete. The other type is post-tensioning, and basically this is leaving the hole here, putting our steel tendon through there, pulling it tight with a jack, and then locking it into place. And it's most common for like double T's. You see these in parking garages all the time, or a single T, hollow core slabs, solid flat slabs, and then these various types of beams. And like we said, one downside is there has to be a restriction to the weight and the size, because you have to transport it into place if you're casting this at a plant. But if you are casting at a plant, one advantage is you can cure it with steam. We talked about the advantage of that just a little bit ago. So you'll have a higher strength, good solid concrete. You get a control for those issues. You can also have a quick turnaround time, especially using this type 3 cement. Remember, type 3 is a high early strength concrete. So use that type of cement, and you can get them out of the plant quickly. And like I said, it's easy to do this in this controlled environment. So as far as adding this pre-stressing, it is typically modular, meaning you get the same form, and this plant might produce the same thing over and over. That's the only cost-effective way to do it. They wouldn't be creating a whole new operations for every single site. So it would be these standard-sized members that you would be working with. This is the opposite of a site cast unit. Usually tilt up, where we see here, where we're casting it on the ground, and you pour it almost like a slab on grade, but you change your reinforcing in order, because you're going to have to tilt it up, and it's going to be working as like a vertical wall as opposed to a slab on grade. Just like before, you want to put in your reinforcing steel and your embedded items, and make sure you have a release edges so it comes off of the forms. Strip those forms, and then you can see them hoisting it into place. So that's what I have for this one. I hope that was informative, and I look forward to talking to you all next time. Thanks.